At this exact moment, inside this massive production line, one technical decision determines whether 2 million toilet paper rolls meet quality standards or become industrial waste. The choice happens in less than 3 seconds. Temperature, pressure, timing. If any of these parameters shifts by just 5%, the entire batch fails. This is where engineering precision meets mass production at an insane scale. And this decision is made every single minute of every single day. This facility produces over 2 million toilet paper rolls every 24 hours. That's roughly 140 rolls every single minute, non-stop. The raw material entering this factory is recycled paper pulp mixed with virgin wood fibers. What leaves at the end is a finished product wrapped, packaged, and ready for global distribution. But between those 2 points, there are multiple stages where one wrong move disrupts the entire flow. We're not here to walk through every step. We're here to understand the critical decisions that make this mega factory operate without failure. The production line is divided into 4 main zones. Zone 1, pulp preparation and fiber blending. This is where recycled and virgin fibers are mixed with water to create a uniform slurry. The ratio here is not random. It's calculated based on the desired softness, strength, and absorption rate of the final product. Zone 2, sheet formation on the paper machine. The slurry is spread onto a massive moving screen, where water is drained and fibers start bonding. This is where the first critical decision happens. Zone 3, drying and creping. The damp paper sheet passes through heated cylinders. This is where moisture is removed and texture is created. Another critical decision point. Zone 4, slitting, rewinding, and packaging. The massive parent roll is cut into smaller consumer-sized rolls, wrapped, and prepared for shipment. Final decision zone. Each of these stages exists to support one thing: consistent quality at high speed. Now, let's break down the decisions that control everything. Critical decision number 1, fiber consistency control during pulp blending. Inside the pulp blending tank, recycled paper and virgin wood fibers are mixed with water. The target is a slurry with a fiber consistency between 3 and 5%. From an engineering perspective, this percentage is everything. If the consistency is too low, the fibers won't bond properly on the paper machine. The sheet becomes weak, tears during production, and creates massive downtime. If the consistency is too high, the slurry becomes thick and uneven. The paper machine can't spread it uniformly, leading to inconsistent thickness and texture. Here's the decision. Automated sensors measure the slurry density in real time, and the system adjusts water flow within seconds. But this is where process stability is tested. If the recycled pulp batch has higher moisture content than expected, the sensors must compensate instantly. If they don't, the entire blend is off and production stops. In industrial practice, this control loop runs continuously. The system doesn't wait for a human operator to notice the problem. Because at this scale, waiting 3 minutes means losing 20,000 rolls. Think of it like this. If you're making bread dough, you can feel when it's too wet or too dry and adjust by hand. But when you're producing enough material to cover 6 football fields every hour, there's no room for guesswork. This decision happens automatically, but it's built on precise engineering logic. The blend must be perfect before it reaches the paper machine. No second chances. Critical decision number 2. Vacuum pressure on the forming screen. Once the slurry reaches the paper machine, it's spread onto a moving wire screen. This screen is about 6 meters wide and moves at speeds exceeding 1,000 meters per minute. That's faster than a Formula One car at full speed. Underneath the screen, vacuum boxes apply negative pressure to pull water through the mesh. The decision here is about suction strength. Too much vacuum pressure, and the fibers are pulled unevenly. The sheet develops weak spots and holes. Too little vacuum, and water stays in the sheet. It becomes too wet to handle in the next stage, and the drying cylinders can't keep up. From an engineering perspective, this is a balance between speed and quality. The vacuum level is adjusted based on the machine speed, the fiber type, and the ambient humidity inside the factory. In modern facilities, this adjustment is automated. Sensors monitor sheet formation and adjust vacuum pressure in real time. But here's what's often underestimated. If the pulp consistency from Zone 1 was slightly off, the vacuum settings in Zone 2 must compensate. This is why every decision in this process is connected. One small deviation creates a chain reaction. Industrial operators don't just control one variable. They manage a system where every parameter affects the next. This control exists to ensure that by the time the sheet reaches the drying section, it's already at the right moisture level and fiber density. And at 1,000 meters per minute, there's no time to fix mistakes downstream. Critical decision number 3. Yankee dryer temperature and creping blade angle. The damp paper sheet now enters the drying section. At the center of this stage is a massive heated cylinder called the Yankee dryer. It's over 4 meters in diameter, internally heated with pressurized steam, and operates at surface temperatures between 90 and 110 degrees Celsius. The sheet is pressed against this cylinder and dried as it rotates. But this is where the texture of toilet paper is actually created. As the sheet leaves the dryer, it passes under a metal blade called the creping blade. This blade scrapes the paper off the cylinder at a precise angle, creating thousands of tiny folds. These folds give toilet paper its softness and stretchability. The decision here involves 2 parameters, dryer temperature and blade angle. If the temperature is too high, the paper dries too fast and becomes brittle. It loses softness. If the temperature is too low, the sheet stays damp and sticks to the cylinder. Production stops. The creping blade angle controls how much the paper is compressed and folded. A shallow angle creates minimal folding. The paper is smooth but not soft. A steep angle creates deep folds, but if it's too aggressive, the sheet tears. Here's where precision becomes critical. In industrial practice, these 2 variables are adjusted together. The dryer temperature is set based on machine speed and the moisture content of the incoming sheet. The blade angle is fine-tuned based on the desired softness level. Here, small deviations create large losses. If the blade angle drifts by just 2 degrees, an entire production run can end up outside quality specifications. That's 30,000 rolls per hour that can't be sold. That's why modern systems use automated positioning and real-time monitoring. Operators don't manually adjust the blade every hour. The system does it continuously based on sensor feedback. This decision is often underestimated because the effect isn't immediately visible. But after 10,000 meters of paper, the difference is obvious. And in a facility running nonstop, that difference compounds every single hour. Critical decision number 4. Tension control during slitting and rewinding. The dried paper sheet is now a massive parent roll, sometimes over 2 meters wide and weighing several tons. This parent roll must be slit into smaller consumer-sized rolls. The machine cuts the sheet into multiple strips, typically 8 to 16 at a time, and rewinds each strip onto individual cardboard cores. The decision here is about tension control. If the rewinding tension is too tight, the paper compresses. The roll becomes hard and dense, and when the consumer unrolls it, it doesn't tear cleanly. If the tension is too loose, the roll is soft but unstable. It can collapse during packaging or transportation. From an engineering perspective, this is a dynamic control problem. As the roll diameter increases, the tension must decrease slightly to maintain consistent density. The system adjusts tension in real time using load cells and torque sensors. But this control also depends on the quality of the paper coming from the dryer. If the sheet has inconsistent thickness due to earlier process deviations, the tension control becomes unstable. This is why every stage matters. In high-speed production lines, slitting and rewinding happen simultaneously on dozens of cores. Each core must have identical tension. If one reel is off, it gets flagged by automated inspection systems and removed from the line. This decision is critical because it directly affects the consumer experience. A poorly wound roll unravels unevenly, tears in the wrong places, and creates product complaints. Quality control at this stage is non-negotiable. Across every zone of this factory, Automated systems monitor critical parameters. Fiber consistency sensors in the pulp blending tanks. Vacuum pressure regulators on the forming screen. Infrared temperature sensors on the Yankee dryer. Tension load cells on the rewinding machines. These systems don't just measure, they adjust. If a parameter drifts outside its target range, the control system corrects it within seconds. Human operators oversee the process, but the real-time adjustments are automated. This level of control is what makes mass production possible. Without it, producing 2 million rolls per day would require constant manual intervention, and quality would be inconsistent. In industrial practice, prevention is always cheaper than correction. A batch that fails quality tests is wasted material, wasted energy, and wasted time. That's why every critical decision point is protected by redundant monitoring and automated feedback loops. By the time the finished rolls leave this factory, they've passed through dozens of automated quality checks. Thickness consistency, softness level, tier strength, roll density. Each of these parameters is a direct result of the critical decisions made earlier in the process. If the fiber blending was precise, the sheet is uniform. If the vacuum pressure was controlled, the formation is consistent. If the dryer temperature and creping angle were optimized, the softness is exactly as designed. If the rewinding tension was stable, the roll unwinds smoothly. These decisions also impact operational efficiency. A stable process runs continuously. Downtime is minimized. Energy consumption is optimized. And in a mega factory producing millions of units per day, even a 1% improvement in efficiency translates to significant cost savings and reduced waste. This factory operates nonstop because every critical decision is controlled, monitored, and optimized. Fiber consistency, vacuum pressure, dryer temperature, creping angle, rewinding tension. Each of these decisions happens in seconds, but their impact lasts through the entire production cycle. This is what makes modern mass production possible. Not just speed, but precision. Not just volume, but consistency. From an engineering perspective, toilet paper manufacturing is a perfect example of how process control defines product quality. The difference between a high-quality roll and industrial waste is often just a few degrees of temperature or a few seconds of timing. And in a facility producing 2 million rolls every day, that difference is everything.